So hello everyone, this is lecture number 1. I welcome you again for the second chapter of class 11 physics, that is motion in a straight line. So after units and measurements, let us begin with the new chapter today, that is motion in a straight line. As the name suggests, motion means there is a movement, and only we are considering the complete motion in a straight line. The simplest motion which can occur in the day-to-day life, in the real life, in the physics world is movement in a straight line. So we'll try to understand what are the basic mechanisms regarding this, and we'll try to understand what is basically kinematics. You will rise to a new terminology, a new branch of physics, I suppose, which is called as kinematics. You will understand basic several equations regarding kinematics. We will understand the difference between velocity and speed, acceleration, etc. How to relate these terms, everything will be dealt in this chapter. So just sit back and just enjoy this chapter. So this is the lecture number 1 on motion in a straight line. I'm Samir Lawankar. Let's begin our discussion. Fine. So this is the course outline for your second chapter of the class 11th textbook, that is motion in a straight line. So here we'll start with introduction. Let's directly start with introduction. Let's not go into details of whatever is written in course outline. Then as the topics will go by, we will go with every discussion which is written after this. Okay. So introduction about your this chapter. Fine. So let's start. So motion is common to everything in the universe. Exactly. So we walk, we run, we ride a bicycle. Even when we are sleeping, air moves into and out of our lungs and blood flows in arteries and veins. So this blood flow is also in some motion, either upward, downward, sideways. This air movement is also some motion, right? Maybe curvilinear, maybe rectangular, maybe in a straight line, maybe in a circular motion, maybe back and forth, but some sort of motion is happening there. Similarly, we see leaves falling from trees and water flowing in a dam. So water flow movement of dam is also a motion. The leaves falling from trees is also a motion, right? So they fall due to the action of gravity. Okay. Automobiles and planes carry people from one place to another. So this passage or this transportation from point A to point B is also motion. So it can either occur in linear fashion or in curvilinear fashion, or it can go above and come below. So these sort of things are just motions, different aspects of motion which we try to consider, or which we can try to depict when we understand the terminology or the term motion. Okay. The earth rotates once every 24 hours and revolves around the sun once in a year. So this is also a motion. Let us say this is our earth, and the movement, even rotation and its revolution, both are basically motions only. Only the path of motion or the center of axis of motion is different, but all these things are motion only because we are trying to move from position A to position B. Let's say a fixed point of this on this earth is being has changed its position when we are talking about some time t is equal to 0 and some time t is equal to t. Okay. The sun itself is in motion in the Milky Way galaxy, which is again moving with its local group of galaxy. So even sun is also in some sort of movement. Okay. Motion is, so finally, after all these examples, what we can depict it, what is motion? Motion is basically a change in the position of an object with time. Okay, so motion is basically a change in position of an object with time. So just putting it as an example, let us say there is an object kept here on the ground at t is equal to t1, t is equal to t1, right? And if it moves from this position to, let's say, this position, and let's say this t is equal to t2, then this is said to be that the box was in motion. As you can clearly see that there is a change in the position. So therefore, this was the original position of the object or the box, and this is the final position of the object or the box. Okay. But how does this position change with time? What are the forces considered, or what are the things happening, or what happens internally, etc. We'll try to consider all these different analogies, different aspects into the complete series of lectures or chapters which we'll consider in 11th and 12th class. Okay. So in this chapter, what we will consider, we'll try to describe motion. Okay, so how does this position change with time? In the chapter we shall learn how to describe motion. Okay, so how to describe motion is the basic aspect of this chapter. for this, we develop the concepts of velocity and acceleration. So this may be something new for you all. That is the concepts of velocity, acceleration. You may know, but what is the basic terminology? What is the basic physics behind acceleration terminology? Will be dealt from the very basic. So this is the basic aspect of considering or understanding velocity and acceleration. Please remember, velocity is different from speed. Okay. That aspect will be cleared in much detail after the completion of this chapter. So you will understand very clearly what is the difference between velocity and speed. Okay. We shall confine ourselves to the study of motion of objects along a straight line, also known as rectilinear motion. So as the chapter's name suggests, that this chapter is based upon your complete study on straight line. Therefore, we will only consider all the motion of objects in straight line only. This motion is also called as rectilinear motion. So this is just for your reference part, that this motion is also called as rectilinear motion. So we should confine ourselves to the study of motion of object along a straight line, which is also called as or also known as rectilinear motion. Okay. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. Okay. So what are these equations? This simple set of equations is one of the property or one of the subtopic of this lecture series we are trying to understand. Okay, so let's not go into that discussion right now, but just for your reference purpose, everything is written in introduction. We will try to understand that concept also. Okay. Then next thing is finally to understand the relative motion of so this thing is done. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. So this may be a new terminology for you, relative velocity. So what is basically relative velocity? Let's not go into complexity of relative velocity. Let us just understand that this is one of the concepts which we will try to understand in this chapter. Let us face it, or let us have it being cleared clearly at the end of the chapter. Having mismatch everything creates confusion. So just understand that, yes, okay. So there is a concept called as relative velocity, which we will try to understand when the chapter is going to end. Okay, so this may be the end of the lecture of relative velocity is the last concept which you will study in this chapter on motion in a straight line. Okay. So in our discussions, we shall treat the objects in motion as point object. This is very, very important. This is very, very important. Everything which you are trying to consider, just consider them as point object. Okay. So in a good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. Okay. So due to this consideration, we are considering them to be equal to, or we are considering them to be point objects. In kinematics, we study ways to describe motion without going into the causes of motion. Okay, so that the terminology which I just explained to you when I started the lecture, that is this complete part of what we can say physics, which deals with motion of objects, or which deals with how there is a motion of object from point A to point B. Let's say a straight line, circular line, projectile motion. You will understand projectile motion in, I guess, third chapter, motion in a plane. So these all things are encapsulated in a terminology or in a branch of physics or a subtopic of physics called as your kinematics. Okay. So in kinematics, we study ways to describe motion without going into the causes of motion. We are not going into the causes of motion. We are just trying to describe the motion. Okay, fine. So I guess that was the complete introduction part of what is motion, what we are trying to understand, what are the different topics which we will try to understand. Let's now go into the basic details of position, path length, and displacement. Right? So let's directly jump into the concepts only, then we can discuss forward. Okay. So earlier you learned that motion is change in position of an object with time. So this was the first definition which you understood in the introduction of this. What is motion? Motion is basically change in position of an object with time, right? So that is defined as motion. In order to specify position, we need to use a reference point and a set of axes. Okay, so basically what are axes? Axes you may have known as one of the standard axes which everyone knows is basically your XYZ axis. So this is your X, this is your Y, and this is your Z. So a set of axes basically means that either it can be your standard reference axis, but any three directions can be referred to as your axis. So that is the way how this set of axes is being explained here. Okay, for the easy references for now, you can understand that the set of axes refer here to the standard axis only. Okay, what does a reference point mean? A reference point simply means that, let us say we need to calculate the distance moved by this point to this point. Let's say this object to this object, right? So there should be some value of this position and some value of this position. But from where should we take that position? Generally, when we study graphs, if you have studied in last class 10th, class 9th also, you try to measure everything from the center point value called as origin. This is nothing but called as a reference. So you always need a reference point for your calculation, and that has only been explained. Okay. Fine. So this thing is explained. This thing is explained. So in order to specify position, we need to use a specific reference point and a set of axes. Okay. It is convenient to choose a rectangular coordinate system consisting of three mutually perpendicular axes labeled x, y, and z axis. So that is the only thing this is written here. So I will just try to rub and make it much more clearly. So that rectangular coordinate system. So that rectangular coordinate system is nothing but this only. So this is x, this is y. If x, y is in plane, then this z axis is not in plane. Okay, so just keep that in mind. So this z is out of plane. Okay, so these are the three mutually perpendicular axes. What does it mean by mutually perpendicular? Each of these are perpendicular to each other. Okay, that is simply meaning that is mutually perpendicular, three mutually perpendicular axes labeled x, y, and z axis. Okay, fine. So this thing is explained. Next line. The point of intersection of these three axes is called the origin. So the point of intersection of these three axes is called the origin O and serves as the reference point. Okay, so this is that your origin, or it can also be called as your reference point. Okay, so this thing is explained there. Next thing states that the coordinates x, y, z of an object describe the position of the object with respect to this coordinate system. Okay, so let us say there's an object lying here. So how can we find out the position? So it is some x distance from here, let us suppose. Then it is some y distance from here, let us suppose. And it is some z distance from here, let us suppose. So if we try to plot the value, so this may lie somewhere here. Okay, that this is the position of your what we can say position of the object. Okay, similarly to measure time, we position a clock in the system. So if you position a clock in the system, that can be used for measurement of time. Now this coordinate system, this line is very, very important line. Please look at this line very, very carefully. So this coordinate system along with the clock constitutes a frame of reference. So this frame of reference is a very, very important topic which will be used in the entire kinematics. So what is basically frame of reference? Because understanding of frame of reference is a game changer in many of the concepts you will understand in subsequent topics or subsequent chapters. Okay, so frame of reference. So what is basically frame of reference? The frame of reference is nothing but your coordinate system plus the clock you used. Okay, so if there is a change in the coordinate system, then there is a higher chances that there will be a different frame of reference in which you are working. Okay, so as the things goes by, you will understand clearly much more what I'm talking about. So first, right now, you can just understand it is okay. So there's a concept, there's a new concept which is defined as your frame of reference. What is frame of reference? Frame of reference is nothing but the coordinate system which you understood previously in the first 5 points along with the clock is basically represented as your frame of reference. Okay, fine then. So this thing is also explained to you. Let's start then. The next line. The next line says that if one or more coordinates of an object changes at time, we say that the object is in motion. Quite evident. Let us say only x changes to x dash. If there is a change in the value of x dash only, then there will be motion occurring, because what is basically motion? Motion is change in position of the object with respect to time or with time. Okay. Fine. Next is otherwise the object is said to be at rest with respect to this frame of reference. Okay, so if there is no change in the coordinates, then that object is said to be at rest. Fine. Next line. The choice of a set of axes in a frame of reference depends upon the situation. Okay, so whatever situation may be, we need to align our coordinate axis or our reference axis in such a state so that the calculations or the depiction or the interpretation of the answer or the solution is much more easy. Okay. So fine. So this thing is also explained. Next thing is, for example, for describing motion in one dimension, we need only one axis. Okay, quite evident. So because there is no movement in y or z axis, we can just consider that there is a movement happening in, let's say, left side direction or right direction. Okay, so either it can move left or it can move right. So basically, it just simply means that there is a movement only and only happening. Let us say if we take this in x-axis, and there is a movement only happening in x-axis. Okay. So to describe motion in 2 or 3 dimensions, we need 2 or 3 axes. Okay. So if 2 dimension has been used, then we will use this 2 x and y, let us suppose. And if 3 dimension are used, we will use the complete one, that is 3 dimensions support. Okay. Fine. So for example, for describing that is explained. To describe motion, this thing is also explained. Description of an event depends on the frame of reference chosen for the description. This is very, very important line. So this basically means, so just I will try to put an example. Maybe this may be a little typical for understanding, but what actually happens is sometimes if we change the state of reference, the velocity of the object calculated will be changed. Okay, so I won't go into complexity because that will only make you confused about this concept. So just for now, the importance of frame of reference can be understood as in that whatever event is required, or whatever the criteria or the frame of reference which you are working on depends entirely on the coordinate axis and the clock be used. And sometimes because of change in the frame of reference, there can be change in the solutions or answers also. Okay. So description of an event depends on the frame of reference chosen for the description. Okay, we'll go very slowly. This is not a very out of the world topic. Okay, so we'll go very slowly. We'll understand each and every concept, and this frame of reference will also be easier to understand. Okay, then you can directly apply frame of reference concepts whenever you require. Okay. So, for example, when you say that a car is moving on a road, you're describing the car with respect to a frame of reference attached to you or the ground. Okay, so let me just make that concept here also. Let us say this is the car moving in this direction. Okay, so okay, fine, I'll work it here. Let us say this is the car moving in this direction. So whatever you are seeing in this is nothing but, let us say this is your man or this is your road, right? So our frame of reference is either kept here or either kept on us. So that is basically the concept of frame of reference we explained here. Okay, so if the frame of reference is kept here, then what we can do is, or what we can say is that this is the example being explained here. So everything what we are saying about the car, let's say velocity of the car, or let's say acceleration of the car, is being explained when we are picking a frame of reference with respect to, or we are keeping the frame of reference attached to you, either the person or the ground. Okay, let us say we are also walking in this direction, and I'm keeping the frame of reference as me only. Then the amount of velocity or the velocity which I suppose for the car may change as respect to ground, because ground is in rest condition, I am not in rest condition. Okay, this concept will be much more clear when we will understand the concept of your relative velocity. Okay. Fine then, so this thing is also explained that, for example, when you say that the car is moving on a road, you are describing the car with respect to a frame of reference attached to you or to the ground. Here is simply what does frame of reference mean? It just simply means coordinate axis along with the clock. Okay, but with respect to a frame of reference attached with a person sitting in the car is at rest. Quite evident. Let us say I put the frame of reference here only. Then here the position delta x and delta x at the, let's say there's a watch being kept at the in the car on the opposite of the driver's seat, and the driver is watching the watch. Okay, so according to the, if it doesn't see outside, if let us say there are black tinted windows being occurred outside and the car is moving at some velocity, let us say there is no surround sound being available, we cannot understand whatever is happening outside, then the watch will always be kept at that location only. Let's say time is t is equal to t1 and t is equal to t2. So for the frame of reference, if the frame of reference is attached to, let's say, the person sitting inside the driver's seat or inside the driver, on the driver, then what we can say that the position of the watch has not moved. But let us say if the frame of reference is kept outside, then it is clear that the position of the watch is being moved from this position to, let's say, this position. That is quite in motion. So that is how that frame of reference changes the value of displacement, velocity, distance, etc. Okay. Fine. So that was all the concepts which I was trying to understand from this. The main conclusion from this topic or this slide can be, first of all, you must understand the concept of frame of reference. And second thing, you must understand that we are first here to ease everything. We are just only working on motion in a straight line. So for the entirety of the topic, we will only work on motion in one axis only. Okay. Fine then. So to describe motion along a straight line, we can choose an axis. So let us say we choose the x-axis so that it coincides with the path of the object. Okay. So we are trying to say that we are putting this x-axis on the path in which there is a movement of the any object, let's say a car only. Okay. That's how we are trying to understand this complete situation. Okay. So we then measure the position of the object. How we measure this position? With reference to a conveniently chosen origin, say O, as shown in the figure. So this is that origin or the reference point we were talking about. So this is the reference point. Now we'll measure each and every distance from this measurement only. Okay. So position to the right of O are taken as positive. This is just simple sign convention being adopted. There is nothing. So sign convention can be adopted as a rule, so that whenever the solution comes or answer comes, we can understand that what our answer is towards right side or left side. Okay, this thing can be engrossed to 2 axis, 2 plane also, and 3 axis also. Okay, so sign convention will be utilized in many of the concepts in physics. So just keep on using them, and the rest all thing will be mathematically explained. Okay, so this thing is explained. The positions to the right of O are taken as positive, while the positions to the left of O are taken as negative. As you can see, these are negative, these are positive. Following this convention, the position coordinate of the point P and Q. As you can see, the point P has a coordinate of plus 360 and point Q has a coordinate of plus 240 meters respectively. Similarly, the position coordinate of point R is minus 120 meters. Okay, everything is just quite evident. Very easy topics. All these are. Let us begin further discussions. Now let us go on to the first major topic, which is called as a path. Okay, path length. Okay, let us understand this very clearly, and then we can move on to the consideration of displacement. Okay. So consider the motion of a car along a straight line. Okay, let us see. We are understanding that there is a movement of car along the straight line only. Okay, so we choose the x-axis. Such that it coincides with the path of the car's motion and the origin of the axis as the point from where the car started moving. So let us say the car had moved from this position here. Okay, so that is the car was at x equal to 0 at t is equal to 0. Okay, so this was the position at which the car started. Fine. Now let P, Q, R represent the positions of the car at different instants of time. The time is not given, but we are understanding that, let us say that at some time t is equal to t1, it was at P. At some time t is equal to t2, it was at Q. At some time R, it was at t is equal to t3. Okay. Oh, sorry. At some time t is equal to t3, it was at R. So that thing is also done. Okay. Now consider 2 cases of motion. Okay. In the first case, the car moves from O to P. So let us say this is the direction of motion of the car. Okay. The distance moved to the car is OP is equal to plus 360 meter. Quite evident. So there's a single movement is here. So it's going to be OP plus O0 and 360. 360 minus 0 will be equal to 0. This distance is called the path length traversed by the car. Traverse is basically moved by the car or the movement done by the car. Okay. So this distance is called as your path length traversed by the car. Okay. Now let us see the second case now. What happens in second case? So in the second case, what they're trying to say, the car moves first of all from O to P. Let us say this is the first movement, and then moves back from P to Q. So let's say this is the second movement and it stops here. Okay. So during this course of motion, the path length traverse is nothing but OP plus PQ. So it's OP is nothing but your 360. And this value will be nothing but 360 minus 240, which will give you 120. And just add both of them because we are the path is being traversed, right? There will be no negative sign here. We're first going this direction, we're coming back direction. So everything, so total complete path which you travel is nothing but 360 plus 120, which is equal to 480 meters. Okay. So what does this plus 1? It tells you that a complete path is being done in the positive direction. Okay, fine. So path length is a scalar quantity. So now what are the scalar quantity? What does it try to depict you? For now, just understand a scalar quantity is a quantity that has a magnitude and has no direction. When direction comes into picture, those quantities are called as a vector. Okay, vector will be dealt in very detail in the next chapter, that is motion in a plane. So don't be hesitant about this. We will understand each and every topic clearly. So path length is a scalar quantity. The only it's a way to measure different types of things. Some sorts of concepts or quantities which are available in physics are scalar quantities. One way to explain this scalar quantity is that scalar quantities can be directly used in algebraic operations. So you can directly add a plus b is equal to 20, let's say 20 and 30, so it will be 50. But same thing cannot be occurred for vectors. The vector addition, vector multiplication, vector division, vector subtraction are some sort of different. Okay, so when the time arises, we will understand vector. But for now, what we understood is that okay, so there is something called a scalar quantity. What is scalar quantity? What we understood that it is a quantity that has a magnitude and has no direction. So one of the example which we got for scalar quantity is path. Okay, so you don't need to think about anything about vector right now. Just keep it back in the mind that okay, there may be something which will come in future which is called as vector quantity. We'll try to understand this vector quantity when the time arises. Okay. Fine. So final conclusion of this topic is that path length is your scalar quantity. Okay, so a quantity that has a magnitude only and no direction. Okay, now let's move to the next topic, which is displacement. A new topic, a new word comes into picture now to understand what is displacement. Okay, so it is useful to define another quantity which is called as displacement as the change in position. So this is also change in position also. This also may have some units in meter, centimeter, etc. only. But this is something different from path length, which you are trying to understand in the subsequent points. Okay. So let x1 and x2 be the positions of an object at time t1 and t2. Okay, then its displacement denoted by delta x is in time delta t is equal to t2 minus t1, which is given by the difference between the final and the initial positions. Okay, so what is the basic definition? What we understood is, let us say there is a at x1 was the displacement of the not a displacement, sorry. X1 was the position of the object at some time t1. X2 was the position at some time t2. Okay, so displacement denoted by delta x. So this is the sign for delta is equal to x2 minus x1. Okay, so that is the basic definition of your displacement. Okay, so we use the Greek letter delta to denote a change in quantity. Okay, so this thing I have explained you. So this is basically delta. Triangle is being used as or called as delta. It's a Greek letter and that is used for telling something about change. Okay, always remember, change is always and always calculated as final minus initial. Okay, so here it is obvious that x2 would have occurred at some time which is greater than t1. Okay, so t2 is greater than t1. Generally, if it is not given, then we assume that t2 is greater than t1, and therefore x2 will be a value which would have occurred after time t1 only, at some time t2. Okay, now this x2 can be either backwards or forwards or at the same position. That is different scenario, but just I'm trying to explain that. Okay, so delta x will be always your final value, that is x2 minus initial value. Okay, because we cannot go back in time, right? So we always move forward in time only. That's why as it is t2 minus t1, as you can see above also, that delta t is also t2 minus t1. Okay, that's final minus initial. Okay, fine. So this thing is fine. Let's move on. So if x2 is greater than x1, as you can see, just keep on seeing this formula here. So if x2 is greater than x1, it is quite evident that delta x value is positive, right? Because x2 will be greater than x1 and delta x will be positive. Similarly, if x2 is less than x1, then delta x will be negative, right? Now, the thing to consider is displacement has both magnitude and direction. Okay, so using the sign conventions, we can understand that the movement of the object has finally moved either to the right hand side direction or it has moved towards the left hand side direction. Okay, hence displacement is one of the example of something which I referred earlier, which are called as vector quantities. Okay, we'll understand vectors in very detail in the next chapter. For now, just keep this in mind. Okay, so there was something called as path length. Path length was a scalar quantity. Now we understood something in the same scenario of change in position also. It's also measured in meters only. It's also type of length only. But this is a vector quantity. This has both magnitude and direction. Magnitude means basically the number which is associated, right? And the direction is basically using some sign convention. We can understand what is the movement from the or what is the direction or in which way the object is going from the origin or the reference point. Okay. So such quantities are represented by vectors. So that thing is only been explained here. Presently, we are dealing with motion along a straight line, also called as rectilinear motion. Okay, this thing was explained in introduction also. In one-dimensional motion, there are only two directions. One is backward, one is forward. Quite evident. You can either go in this direction, you can either go in this direction. There is no other direction, right? Or either let us say we are working in this direction, right? See, so we can go either upward, either forward. Sorry, downward. Okay, so these are only directions available. Okay, in which an object can move, and these two directions can easily be specified by plus and minus sign. So, proper sign convention says that when you are going towards right, we say it as positive. When you go towards left, it is said as negative. So when you go up, it is said as positive, and when you go down, it is said as negative. Okay, so they are similar to the convention that you follow for your, let's say, XY graph, which you make graphs, right? So graphs also have the same convention. Okay, fine. Moving on. So, for example, let us go to the look at the examples of displacement. Okay, for example, displacement of the car in moving from O to P. Let us say this was the initial position that was denoted by x1, 1, and this is the final position, that is 2. Okay, so how to calculate the value of displacement? We understood it from the formula. It is delta x, which is equal to final value, that is x2, minus initial value, that is x1. What is the value of final value? It is 360 in the positive direction. So we will write plus 360 minus initial value is 0 only. So therefore the final answer is plus 360. Okay. So for example, the displacement of the car moving from O to P is delta x is equal to x2 minus x1, which is equal to plus 360 minus 0, which is plus 360 meters. Okay. So what does the plus sign shows here? Plus sign simply shows that what the direction which we moved from moving from O to P, this was the direction which we moved. Okay. Okay, so this thing is also explained. Moving on, the displacement of the car from P to Q. Now we need to calculate the displacement of the car from P to Q. Let us understand from the diagram first. Let us say P was the initial direction. So we wrote this as 1 and this was the final value or final point. This was as 2. Okay, now what we will do, we will write it again. So delta x is nothing but equal to x2 minus x1. What is the value of x1? What is the value of final value? x2. x2, as you can see, is plus 240 because it is on the right hand side direction. And what is the value of p? x1, that is plus 360. Right. So just solve this. You will get the answer is equal to minus 120 meters. What does it depict? That from the initial position, this was the initial position. In which direction will you move? If you will move on the negative direction, 120 meters, then you will reach the position Q. That is the depiction of this complete concept. Okay, so these all things are explained. So what the negative sign shows here? The negative sign indicates the direction of displacement. Okay, thus it is not necessary to use vector notation for discussing motion of objects in one dimension. Okay, so in one dimension it is not required, but when we try to increase dimension to 2 or 3, then it is very important to understand vectors also, and the way vectors tell you about the directions. Okay, so thus it is not necessary to use vector notation for discussing the motion of objects in one dimension. Next line says that the magnitude of displacement. What does the magnitude mean? Magnitude is basically the value which comes. So let's say what is the magnitude of the first displacement? It's plus 360. And what is the magnitude of second displacement? It's minus 120. Mod of these magnitudes will give you, let's say, 360 and 120 meters. Okay. So the magnitude of displacement may or may not be equal to the path length traversed by an object. Okay. So this can be quite clear, but we'll use one of the example and then we can understand this much more clear. Okay. Example written on the next line only. For example, the motion of for the motion of the car from O to P, the path length is 360 meters. Quite evident. Displacement is also 360 meters, which we just calculated. So this thing is correct. But this is not always the case. Let us say we change the case now. Let us say we change the case in which we are finding out the displacement and the path length. If we go from O to P and then come back from P to Q, and the path length will be plus 360 plus 120. That will be plus what we can say 480. But same thing won't occur for your displacement. Displacement will be final value minus initial value, which will give you plus 240. It is quite clear that 240 is not equal to plus 4. Okay, so that is how this thing can be explained. So in this case, the magnitude of displacement is equal to the path. Now let us look to the next solution. So now, but consider the motion of the object from O to P and then back to Q. What happens now? In this case, the path length is plus 360 plus 120, which I just explained to you. However, the displacement is, how to calculate displacement? Let us go with very basics. With nothing but delta x is nothing but equal to final value minus initial value. What is the final value? Final value is nothing but plus 240 because it is on the right hand side, minus x1 is 0, which will give you plus 240 meters. So basically what does it mean? That from the initial position, in which direction will we move? If we need to go to Q, so we will move in this direction. Okay, so it doesn't see whether you reach P or whether reach Q any other direction or so. It will just see that you can just move on and keep on. Sorry, it won't see any of the another points here. It will just see the initial and the final. That is the what we can say one of the attributes that displacement for. Okay, so does the magnitude of displacement that is 240 meters is not equal to the path. Okay, the magnitude of displacement for a course of motion may be 0, but the corresponding path length is not 0. Okay, so what do I try to say? That the magnitude of the displacement for a course of motion may be 0, but the corresponding path length may not be 0. So what they're trying to say, let us say we are going from O, we went to P, we went again back to Q, we went to O, we went to R, we went again to O. So if the final and the initial position are same, then the displacement will be 0 because final x2 minus x1 will give you 0. But that this is not the case in terms of your total path length. Okay, as you can see, the path length will be first of all adding up this, then adding up this, then adding up this, and then adding up this. Right. So therefore, quite clear that path length and displacement are something different. Okay. So, for example, if the car starts from O, goes to P, returns to O, and then returns to O, the final position coincides with the initial position, and hence the displacement is 0. Okay. However, the path length of this journey is OP plus PO, which is going from this to this, that is 360. Going returning back again 360. Therefore, 360 by 360 will give you 720. Okay. So that was the explanation about your displacement. Moving on. Motion of an object can be represented in a position time graph. So now let us try to plot some of the graphs so that we can understand the concept much more clearly. First of all, let us see the name. What does the name suggest? The name basically suggests that it's a position time graph. What does it mean, a position time graph? There will be a graph drawn in which the x-axis will be time and the y-axis will be x. X tells you a position, right? So that is the meaning of your position time graph. Okay. So such a graph is a powerful tool to represent and analyze different aspects of motion of an object. Okay, so what are these different aspects? For motion along a straight line, say x-axis, only x coordinate varies with time and we have an xt graph. Quite evident because only x will vary, we don't require even y or z axis. Okay, so let's say we are moving about straight line x-axis, then only x coordinate will vary. Let us say it is varying like this, or it can vary like this, or it can even vary like this. Okay, anything can happen. So to understand this, let us first consider a simple case. Take the simplest case in which an object is stationary. If the object is stationary, let us take few examples. Let us say time is there, and position is there. So if it is stationary, then at some time t is equal, let's say 0, 1, 2. Let's say it is at some 30 meters. Okay, so if it is at some 30 meters, it will always be at 30 meters only. So what we can depict from this, that the position will be always constant, varying upon your time values. Okay, so the position time graph is a straight line. As you can see, it's a straight line parallel to the time axis. Okay, which is as shown in the figure. Okay, so this thing is explained. Next thing is the position time graph is a straight line parallel to time axis. This is done. If an object moving along a straight line covers equal distances in equal intervals of time, it is said to be in uniform motion along a straight line. So the new terminology came called as uniform motion. So what is basically uniform motion? Uniform motion is only this, that if an object moving along a straight line covers equal distances in equal intervals of time, then it is said to be in uniform motion along a straight line. The example diagram for the uniform motion is given on the right hand side below. That is the position time graph of a straight line uniform motion. Okay, depicting this one in terms of tabular form also. Let's say some t is there, some x is there. So what is actually happening? Let's say 1, 2, 3 seconds, or let's say 4 seconds. So first of all, it went to 5, it went to 10, it went to 15, and it went to 20. As you can see that it covers equal distances in equal intervals of time, even here, and even here. So that is the thing which is depicted. Okay, we can even make one more edit. It was 0 at 0. Okay, so some sort of this has been made. Okay, figure B shows the position time graph of the such a motion. Okay, fine. So let us consider the motion of a car that starts from rest at time t is equal to 0 seconds from the origin and picks up speed till t is equal to 10 seconds. So as you can see from this graph that it is trying to pick up some speed. So this is the position time graph in which it is trying to pick up some speed and thereafter moving uniform speed. How can we say that it is moving uniform speed? As you can see, it is a constant slope. Okay, so constant line is there, straight line is there, so we can say it is constant till how much? Till t is equal to 18. What happens after t is equal to 18? The brakes are applied and the car stops at t is equal to 20 and x equal to 296. So basically when it was 20, it was 296 approximately, and the car has stopped. So if the car has stopped, after this the position, the graph will be parallel to the time. So that is how you can understand the graphs. Okay. So the position time graph for this case is shown in the figure below. We shall refer to this graph in our discussion in the following sections. Okay, so we'll try to, this graph will come up very much higher because as it is a non-linear graph, it will be easy to generalize concepts using this graph. Okay, the previous two graphs were basically the simple cases which can be adopted. The first was that it was at rest, and the second was for uniform motion. This is some sort of uniform, non-uniform motion which will help us in understanding much more concepts. So that was how displacement took place. So that was all about your path length. That was all about your displacement. That was all about different position time graphs which can be made also. Let us start a new topic now, that is average velocity and average speed. Okay, so let us understand this. What is average velocity and average speed? Let us go very slowly and we can understand each and every topic quite clearly then. Okay, so when an object is in motion, its position changes with time. The basic concept which you understood in introduction also. But how fast is this position changing with time? And in what direction? What is the rate of change of its position? Okay, this value is been described by using average velocity. That is how the concept of average velocity came into picture. Okay. Average velocity, let's not be hesitant about what is velocity. Please try to understand these concepts first, and then after this we'll understand average speed, and then we can find out what is the difference between both of them. Okay. So average velocity is defined as the change in position or displacement delta x divided by the time interval delta t in which the displacement occurs. Okay, so average velocity is a function of the displacement and not the total path. This is very important concept to be understood. Okay, so you can see the depiction denotation of average velocity also. So average velocity is written as v bar. Okay, so v bar is nothing but your displacement upon time. This can also be written as equal to nothing but delta x upon delta t, which can also be written as equal to final minus initial upon final minus initial. Okay, generally t1 is took as 0 only, but let us see. Right, so this is the general description. Okay, where x2 and x1 are the positions of the objects at time t1 and t2 respectively. Okay, here the bar over the symbol for velocity, as I explained to you, this is basically bar. This is bar. So this is called as v bar. Okay, so the bar over the symbol for velocity is a standard notation used to indicate an average quantity. Okay, so this is basically used to indicate an average quantity. So wherever you can find the value as v bar, then you can directly depict that value is about your what we can say average quantity. Okay. The SI unit for velocity, is meter per second or ms inverse. Okay, so this is again SI unit you already understood in the previous chapter only what is basically SI unit, and velocity is being the SI unit velocity is meter per second. Okay, although kilometer per hour is also used in many everyday applications. Like displacement, average velocity is a vector quantity. So generally, if quantity is a function of some vector, then there is 100% chance that would if it's not been deducted somehow, then if it's 100% chance that will also be a vector. Okay, so for 11th class purpose you can understand this concept that okay, so this displacement and average velocity both are a vector. Okay, so but as explained earlier, for motion in a straight line, the directional aspect of the vector can be taken care by plus and minus velocity. Okay, so as we are going with the very simple case here, so everything can be taken care by plus and minus signs only. Okay, and we do not have to use a vector notation for velocity in this chapter. Okay, fine. So this thing is also explained. So that we do not have to use the vector notation for velocity in this chapter. Okay. Fine. So let us start now. So let us understand more about this topic. So consider the motion of the car in the figure above. Okay. So figure above as in let us say that there is a movement happening in this scenario. The portion of the xt graph between t is equal to 0 to t is equal to 8. This is your t is equal to 0, t is equal to 8 is blown up. So it is being magnified and shown in the figure below. As you can see, this is being magnified and shown here. As seen from the plot, the average velocity of the car between t is equal to 5 and t is equal to 7 second is what? So v1 is nothing but x2 minus x1 upon t2 minus t1. What is the value of x2? Final value 27.4. What is the initial value? It's 10. What is the final value? It's 7. What is the initial value of time? It's 5. Therefore, it's 27.4 minus 10 meters upon 7 minus 5 seconds. Hence the answer will be 8.7 meter per second. Fine. Okay. Geometrically, this is the slope of the straight line P1, P2. So there's a concept called as slope, which you will understand in maths also. So basically, what is slope? Slope is nothing but a tangent. Okay. So tan theta is also called as slope. Okay. So if you try to find a tangent of the slope P1, P2, then that is also called as a slope. Okay. Geometrically, this is a slope like in the position P1 to the final position P2 as shown in the figure. Okay. The average velocity can be positive or negative depending upon the sign of the displacement. Quite evident. So it depends upon whether this value comes out to be positive or negative. So if it comes out to be positive, then v bar is positive. If it comes out to be negative, then v bar is negative. Okay. Also this value can come out to be 0 also. If it is 0, it is 0 if the displacement is 0. Okay, because time cannot be 0, right? Time is the quantity. It will not be 0. It will have some many value if you are trying to find out the position. Time will always go on. So it is 0 if the displacement is 0. Okay, fine. Let's move on with the concept of average speed. Okay, so figure shows the xt graph of an object for an object moving with positive velocity, and figure A is telling you about moving with positive velocity. So here velocity is positive, here the velocity is negative, and here is dash dash. You can also see that the slope is positive here, the slope is negative here, and slope is 0 here. That can also be understood as to why these type of graphs are having a positive velocity, negative velocity, and set rest. Okay, so slope only tells you about the velocity, and hence that can also be understood here. Next line states that average velocity as defined above involves only the displacement of the object. We have seen earlier that the magnitude of displacement may be different from the actual path length. Quite evident. To describe this rate of motion over the actual path, we introduce another quantity called as average speed. Okay, so average speed, if you can infer, what is basically it is total path covered, total path path length upon the total time taken, total time interval. Okay, so average speed is defined as the total path length traveled divided by the total time interval during which the motion has taken place. Okay, so that is how you can understand the complete concept of your average speed. So average speed is nothing but equal to your total path length upon total time interval. Okay. So let me stop the lecture here only, and then we can move on with further discussions about average velocity, average speed in the next lecture. Okay, then we'll do some of the questions, and then we can move forward with the acceleration and different concepts regarding this topic. Okay, so right now we have completed the introduction part, and right now we have a second point, that is position, path length, and displacement. Okay, so position is being covered, path length and displacement is being covered also. And so this thing is also covered. We are finally right now on average velocity and average speed. Okay, so average velocity is being understood. Right now we are understanding average speed. Then we'll move on to what is instantaneous velocity, speed, and acceleration concept will be understood. And finally we'll move to the main topic, that is finding the kinematic equations. There are the basic three kinematic equations which we'll be using for uniformly accelerated motion. And finally we'll close the topic with relative velocity. Okay, so that's all which is this topic, this chapter has to offer. Let's go very slowly and understand each and every topic, because this is the basic building block of your physics for kinematics. Okay, so thank you so much. Let me stop it here. I'll meet you in the second class. Thank you.